Hello, ladies and gentlemen. If you're here for the title, Entanglement in Dark Matter, you're at the right place. I will give a new idea for dark matter and the way to test it, and I will explain entanglement without violating locality and the speed of light. That doesn't exist anywhere else in the world. But there's 15 other questions I will answer, and I'm going to read what they are quickly. First half, an explanation with words and pictures for how electromagnetic radiation is converted to an electron-positron pair and their composition and structure. Where 1/2 spin comes from and how it is converted to full spin in the electron structure, and this explains the strong magnetic moment and the fact that the electron doesn't rotate itself. Why matter has so much energy, an explanation for decoherence in the measurement problem. Explain the two-slit experiment. Fully explain two-electron entanglement without violating locality and the speed of light. Explain what quarks are made of. Explain what happened to all the positrons. Show the exact structure of neutrinos, both particle and antiparticle structures. Second half, using loop quantum gravity, explain theory of fields and what electric fields are and how they actually produce attraction and repulsion, and law with rules to apply to such actions. Explain for how an electron can change orbitals without actually jumping, how a proton really works, a method used to calculate the mass energy equivalent of a single graviton, a new explanation for dark matter and dark energy. Einstein was once asked about understanding fundamental particles, and he replied that he would just like to understand the electron. Others have said if you understand the electron, you can understand many other things, and that's really proved true. The best starting place is to examine information from an actual experiment, thereby tying the information to reality. The best experiment for this would be the cloud chamber experiment by Carl Anderson in 1932. Picture below is of a cosmic rays interacting with a nucleus to produce an electron-positron pair. A magnet positioned below the cloud chamber causes the electron created to spiral in a clockwise direction and the positron to spiral in a counterclockwise direction. It shows the fact that when energy is converted into matter, it always produces matter and antimatter. This shows high-frequency electromagnetic radiation passing near a nucleus can be converted to an electron-positron pair. Every day at hospitals, positron emission thermography is occurring. PET scan. It's a gamma imaging technique where you have a sugar with a fluorine atom, and it's excited until it radiates positrons. You put it in the patient, and the positrons meet an electron and send out gamma rays. So this is the exact reverse of this, and this shows visual confirmation that this process is accurate. If this was is such a position, it should be persuaded to consider this idea, and in fact Feynman represented electric charge by assuming a pair of spherical inward and outward electromagnetic waves. It's advantageous to check on a radiation produced by a dipole, and this would be the result of a single electron. If it started up this way, if you don't realize it, the regular particles in our universe obey the left-hand rule right here. So as the electron goes up, it produces electric charge, and then there is a half spin clockwise. Then when it turns around to go back down, produces this part, and this represents polarity. This is one of the factors that allows the above reactions produce to go forth. Now, this is a model of the radiation. That's a single wavelength. That's electrical. This is the magnetic clockwise and counterclockwise. So electromagnetic radiation has both half spins, but when you get to an electron or positron, they are credited with only a half spin, and we'll show how the other half gets nullified. Now this can turn 180 degrees, so if you turn it 180, you get this position. And these forward leading positions of the photons, of course they can be much longer, determines the polarity and the spin, whereas this is clockwise, this is counterclockwise. So if we go back up, so now we have the information we need to show a picture of the above process. And this is a situation where you have all the different orientations, and the processes that produce these waves produces them in a form of unpolarized light, meaning you get all the different orientations. And of course here's a longer piece of a photon with a beginning and an end, and it can have different frequencies and different lengths. And here is a representation of the process up there. This represents the normal matter with a clockwise rotation being bent round in a circle, and this of course is the counterclockwise, and that produces the two different particles. Now you can see that to create a particle, the radiation would just continue on unless it forms a circle. Once it forms a circle, it creates a particle, and that particle is bound by the laws of special relativity. Now you have both spins. Here's the clockwise and here's the counterclockwise, and they're for the normal matter, the clockwise would amplify the clockwise half spin, but it would tend to cancel this anti-spin, and so you end up with just one half spin that the electron has. But because this is circling the same direction as the half spin clockwise, that makes, and it's moving at the speed of light, this whole thing, plus this is half spin is too. So that's why the magnetic field is so strong. Now if you make a positron, it's a mirror image of the electron, and proof of that is if you can see this. If you see it this way, it's clockwise, but in the mirror it's counterclockwise. So matter and antimatter are mirror images of each other, and that's how they are produced from that difference. And so why does matter have so much energy? Well, if it's made of a trapped electromagnetic radiation moving at the speed of light, that's a pretty good answer. And we already have shown the strong magnetic moment. And these are all these different explanations based on the structure are offering proof that electrons and positrons are made of electromagnetic radiation. But here's one of the most amazing parts. If you look at this, and the electron, we're talking about it going up to produce this, how do you produce a half spin? The electron can't spin halfway around and stop, so it comes from its internal structure, and this proves that the electron itself isn't producing the magnetism by spinning, but it comes from its internal structure, and in the form we have just already shown you. So if this is the correct structure, it should explain all kinds of things that haven't been explained. And I've mentioned these two and the spin. Now, the reason you get both particles is if you look at the mass of an electron, it's 9.1 times 10 to the minus 28 grams. Well, if you look at the conversion of those grams, you get 5.11 million electron volts per centimeter speed of light squared. If you convert that to frequency, E is equal to HF. You just divide the energy by Planck's constant right here, and you get 1.24 times 10 to the 20th single wavelengths. So here's that number. It's gigantic. So what that says is, when these radiations come in, you'll have enough with all the different orientations to produce the electron and the positron, because there'll be plenty of each orientations. Okay, the wave-particle duality. Everybody has a fit with that, but it's so simple. Electromagnetic radiation comes along, you bend it into a circle. Here's the wave, here's the particle, and in this form it's the wave-particle duality. Now they have a measurement problem and position probability. Probability is the square of the wave function, and let us look at this pictorial. You can see in the center this is a hydrogen atom. That's the nucleus. But here's one wavelength. There's 10 to the 20th power of these. So of course this, I can't represent that many. This is a tiny sliver of here. But if you look at the wavelength here, square it, because it's a wave, up and down, positive and negative. You need it squared to get the absolute value. Now they wonder why, when you measure here, you collapse this, and it's called the decoherence of the wave function. And yes, the wave function does represent the structure. So when you collapse that with some measuring probe, you get a measurement of an electron at this position. But then you can also measure way over here, and you get the same thing, and they wonder, how does it do that so fast? Well, if the electron is only about 10 to the minus 13th of a centimeter, and speed of light is 10 to the 10th, then that's 10 to the minus 23 of a second for all of this to collapse here or over here. So that explains the measurement problem, a way of the measurement problem. Next is decoherence. Well, that's just the same thing, only now that's representing the entire structure collapsing down there, and it's the same thing. It moves at the speed of light without mass to that spot very quickly. The two-slit experiment. There was some Feynman always said, Richard Feynman always said this was a defining example of quantum mechanics weirdness, part of it. But you send an electron to two tiny slits, and on the other side you get a diffraction pattern, and you make the speed so that only one electron gets there at a time. So to get a diffraction pattern, you need the electron to seemingly go through both slits at the same time. Well, now we don't have a problem, because if it's made of electromagnetic radiation, this is massless bosonic material moving at the speed of light, and it can split up and go through part of it through each slit. And when that happens, you get a diffraction pattern like this. Now, most people, here's the setup, and here's the two slits. and it's just that the electron is so much bigger than they think, and it's made of this material that it can break into two parts and go through each side. Now what they don't even ask about is one of these dots represents where the diffraction pattern will suddenly collapse to produce an electron. Well, in between are less of the structure, and the darkened pieces are more intense pieces of the structure. So how do they all come together to fall at this point? And the answer is they're entangled. And electromagnetic radiation is the entanglement factor, and they don't ever seem to know that in regular entanglement. But we're going to cover that. But that's how that works. Okay, entanglement is the really strange of all. Einstein hated entanglement. He understood it. The quantum mechanics, mathematics, declared that if two particles were entangled with two characteristics and then separated, and you measured one of them, either one, that the other particle would instantaneously know the value that the first particle gave. And they have done measurements that concluded 10 times the speed of light would have to be a signal sent from the measured particle to the one to be measured. But they are connected together, and I'll go through this to show how it can be accomplished without violating locality or the speed of light. Let's pick two electrons with an up and a down spin orientation. They entangle, they separate, and now each electron has half of each different spin structure as required by the 50-50 result of any measurement. You can get a down. If you measure, you might get a down or you might get an up, and that's true if you measure this one up or down. But the quantum mechanics equations say these two are connected, and if these are electromagnetic radiations, and also when you start out up and down, you end up with up and down, or you can switch places, but you preserve those structures. And that's accomplished because in here you have bosonic electromagnetic radiation that easily mixes and can come apart with part of the structure here, part of the structure here for the up, and then part of the structure here for the down, and part over here. But they're both connected, they're both preserved, and it's moving at the speed of light between them in a cyclic repeating manner. So let's look on down here. It has a little better picture. Wait a minute, I went past it. Okay, so here they are down here, and let's assume that this is just a, these could be actually mixed together, but let's say this is the structure for the up spin, and this was the structure for the down spin. Now this is repeating and containing itself, so you stick a probe over here, and let's say you trigger the down spin. Well, if the definition of a measurement is a total collapse of the wave function, then as this goes down to collapse the wave function, it has to retrieve the other portion of its structure from over here and bring it over here and go down. Well, look what happens. Just as you break away from this with the last bit of this down structure, you no longer have it connected here, and the only thing you have over here is the up structure. So in that instance, when it breaks away, it knows what it'll be and what this one over here is. But this one hadn't even gotten down over here to give an answer, assuming that the measurement depends on the total collapse of the wave function. So it actually knows not only when it breaks away what it's going to be, it doesn't know, it not only knows that instantaneously, but it actually knows it slightly before instantaneously, because this has to go travel over here. And that time period is a function of how far they are apart at the time your first measurement is conducted. So there is no violation of locality or the speed of light, and all the boxes are checked. Now I estimate that how far apart can these go? Well, with 10 to the 20th power pieces of single wavelengths, that would allow then, in my estimation, to separate 186,000 miles. That's 7.5 times the Earth. And none of these have been even close to preserved in traveling anywhere near that distance. Okay, let's talk about the structure of a quark. There is the reaction where a neutron, being more massive than a proton, because it's two down quarks, which are more massive than the two up quarks, decays to produce a proton. What happens is the down quark, which contains a 1/3 minus charge, tears apart its structure. It rips out 2/3 minus charge from its structure and combines it with a 1/3 to produce an electron. And there's extra energy involved in a electron antineutrino. Now, to make the up quark, you need a plus 2/3 charge. So all of this can be accomplished from the electromagnetic radiation. This represents electromagnetic radiation. This is the electric and the magnetic. Well, if you break it apart anywhere in here, say you break it apart here, then you're going to create the leading edges of an electron and a positron, just like we showed before. And so that explains the structure of a quark. It's also made from electromagnetic radiation. Okay, let us explain where have all of the quarks gone to? Where have all the positrons gone to? Okay, if you look at a proton, you got an up quark plus 2/3 charge half spin, and an up quark 2/3 plus half spin, down quark minus a third charge and a half spin. They actually should label the spins because one of them's clockwise, one of them's counterclockwise. I don't know why they don't. But the total is a +1 charge with a half spin. And I'm telling you, it's the positron. And that's where all the positrons went to make protons in the beginning. And that's a perfect balance. Now, how are neutrinos created? All right, what are neutrinos' structure? The neutrino is tied to the electron. So if this is a single wavelength represented just from here to here of the electron, the neutrino is like it, except it has no positive charge. Here's your positive charges. There's your neutrino. Now, look what we have. I'm going the wrong way. Now, we have the neutrino. And if its leading edge is clockwise, you have the regular, this is the precursor to forming the particle. But that is the regular particle. Here's the antiparticle. Now it is a particle when you bring it all together, and so you can produce the different particle and antiparticle neutrino. And the reason you know it's a particle, because it's measured up north, like underground with the water reservoir with detectors, and when the speed of light there is a lot slower than space, some of these neutrinos, or most of them, are traveling faster than the speed of light in the water, and they crash into it and they're slowed and emit Cherenkov radiation. It's equivalent to breaking the speed barrier, the sound barrier, and it just blasts out an electric light pulse. Now you think it took them a while to realize the neutrino has some mass, but its energy is just slightly less than 1 electron volt, whereas the electron is 500,000 electron volts. So let's just say it's 1,000,000 times weaker than the electron. But the electron has 10 to the 20th power single wavelengths. So if you reduce it by 1,000,000, it's still 10 to the 14th of these single wavelengths. So I would say the neutrinos are really quite a bit there. This ends the first half. Thank you. Hello. This is the second half. I'd like to talk about a picture of an electron. And this was developed by the Lund University Faculty of Engineering in Sweden, where they had lasers, very short pulses. Out of second pulse is 10 to the minus 18 seconds. And they used a combination stroboscope technique which combined these rather weak pulses to form a picture, and here it is. It's pretty amazing. I want to use this structure to represent electron and positron. They're, essentially the same looking kind of a structure, and I will use it to help explain the fields and how they actually operate, as opposed to saying you got a positive and negative field and they attract, or the same fields repulse each other. That doesn't explain how it works. Okay, let's look at an electron and a positron. They come together from attraction and they destroy each other's structure, and when they do, they emit the radiation they were formed from, gamma rays. So to explain this, let's look at nature of space itself, which we know is full of energies. The best experiment expressing this is the Kashmir plates experiment. Two metal plates close together, exclude energies between them, anything greater than a half wavelength and particle pairs and things, so that the energy between them is less than the energy of space outside, and this is a force against the plates pushing them together. And that's what happens here, because this is the regular particle rotating clockwise structure. This is the positron rotating counterclockwise, and they collide their outer edges and start producing radiation that leaves the scene, and that exclusion of the structures too is similar to this setup, so that energy between the two is reduced relative to the energy on the outside, and they're attracted together. Here's two Feynman diagrams. You find these all over the internet, and you have two electrons repelling each other by emitting a photon between them, or considering the virtual photons between them. Well, that's just like putting more energy between the two as opposed to the energy on the outside, so they're pushed apart. So I made this Feynman diagram because it's hard to find one of attraction, because they don't seem to understand it. They talk about virtual photons as helping the attraction, which is just the same as this and would be repulsion. And why they don't consider this as that normal particle of interaction for forces is emitted and flying away to reduce the energy between the particles, and then the outside forces push them together. So there you can make a little law for this. When the energy between particles is greater than the energies on the outside of the particles, repulsion occurs. And when the energy between particles is less than those energies on the outside of the particles, attraction occurs. So what happens when an electron meets the nucleus of a hydrogen atom? Then you have the escaping positron-like structure from the nucleus interacts with the electron's negative and the two rotation clockwise and counterclockwise. You start destroying the structure of the electron, and actually what's coming out really. But anyway, that energy that flies away, 13.4 electron volts, means you reduce the energy between the two, and they're attracted, and the electron is so light it's pushed on top of the nucleus. Now it doesn't continue to destroy, because here it runs into this high energy short range forces, so you just get a small amount of the electron destroyed. And so now they have the saying that an electron cannot jump orbits, that it just appears there for something to do with the quantum calculations. So of course this represents the electron. There's one wavelength, and there's 10 to the 20th of these, so this is just a little piece of the representation. But if you add energy to make the electron jump from one orbit to another, there's no particle to jump. You're just adding energy to this whole structure, and it'll receive amounts that represent electromagnetic that doesn't destroy the structure but has resonance of the quantum levels. Now let's take a stronger look at the nucleus. Now if you want to know what the quarks contain, they contain a flavor of high frequency radiation unique to the type of quark, and they temporarily accept red, green, and blue energy. And if it's an up quark, it has the plus 2/3 of a positron. If it's a down quark, it's a minus third. But here's what's really going on to create this strong confinement force. The gluons, which are combinations of anti and regular color forces. If the quark's red, and the anti-red will be attracted to it, because this is just like particle and antiparticle, clockwise, anti-clockwise, as you just keep repeating this stuff. So it destroys it and emits it so that it comes free. And then the blue, it comes over and attaches itself here. So in effect, both of these energies between these two, the gluon attraction, are disappearing. So you're removing energy between them, even though it doesn't fly out, it stays in the system. But that means the energies out here are pushing in, and because it's smaller, it's a stronger force. And it's a triplet of this stronger force. And that actually is the stronger force. And let's look at this right here. And you see the electron and the interacting with the positive energy coming out, electromagnetic, is like a large Casimir plates. So that there's more energy in there than there is in these nuclear reactions, which is like a smaller Casimir plate. So you already have less energy in between to resist the outside energies. and then you have that triplet energy action, and that all that pressure is the strong force. And this one out, the electromagnetic one, is just 137 times weaker. They're not really all that much difference, and that's where I believe your forces come from. And also, these forces force these three quarks close together. It's hard to do any calculations there. If you add some, say, high energy electrons, you're adding energy between them, and they can separate further because they have more energy to resist the energy pushing in, but it's not enough to overcome them to break free of the confinement. But it follows my little law of adding energy in there to reduce the attraction, and that represents asymptotic freedom, doesn't it? Okay, let us go back to the second half part where we introduced loop quantum gravity. So Albert Einstein created general relativity. He spent the rest of his life trying to unite general relativity and quantum mechanics. He was unsuccessful, and it has not been accomplished yet. General relativity describes gravity, which distorts space, requiring a special quality of space itself, whereas quantum mechanics has more of a static space background. And so to overcome this discrepancy, loop quantum gravity was invented, and it has a Planck length that has significance in this whole theory. Their basic theory is that as you go to smaller and smaller distances, space itself turns into chunks of reality, particle-like existence. And so to sort of support that idea, they just came up with a Planck length. And here's how you describe it. In Welcome to the Universe is a book, and J. Richard Gott explains in there about Planck length. He says, what's the possible fastest clock you can imagine and the shortest time it can make? And so you have a single wavelength bouncing back and forth between two mirrors, and you bring the mirrors closer together, you reduce the distance. That's a shorter wavelength, a higher frequency. A higher frequency is more energy, and after eventually the mass of the photon becomes so large and compressed into such a small space, it falls within its own Schwarzschild radius and forms a black hole. And this separation distance is 1.6 × 10 to the minus 33 centimeters, and that's called the Planck length. And it can be represented and calculated with certain parts describing our fundamental units, like here, and gravity and the speed of light, Planck's constant. So Planck's constant, don't get confused with Planck length. Planck's constant is the smallest energy available, and that represents a single wavelength of electromagnetic radiation. Now, these extremely small connected granular bits do not exist in space. They are considered to be space itself. And so, if they can be considered quantum harmonic oscillators at every point in space, they can generate fields. In fact, this was alluded to by a famous scientist, and their actual size of 10 to the minus 33 centimeters is too small to interact with the regular particles. So you don't have to choose that low a value. You don't want to be close to a black hole anyway. So you can choose a higher value, but not only that, they combine these symmetries. Where is it? This is good, as they are considered to be formed into larger structures of loops, spinners, and foam structures. This is as this brings them closer to fundamental particle size, but more important, you can exhibit symmetry needed to produce identical particles. For example, electrons all with about 10 to the 20th power single wavelengths. If you have lesser energies, you might get the production of a virtual electron and positron pair. Gravity. Einstein took 10 more years to determine his general relativity involving gravity. He determined it was an acceleration and it bent space. And since it's a long range and moves at the speed of light, it's considered to be a massless, and it must be a two-spin boson, because the source of gravity is a stress energy tensor, a second-order tensor. Now, a two-spin boson means that whatever is producing this tiny wisp of energy, of gravity, must rotate only 180 degrees before it repeats its structure, whereas a one spin is 360 and a half spin is 720 degrees. So if we look at the relative strength here, you see that there's some tiny half rotation like that produces the gravity, and we don't know where it comes from or what is it that's moving like that, but I will show a possibility for it a little later. But I want to do a real silly little calculation here just to try to estimate the gram equivalent mass of a graviton. So its description of physicality shape is going to look actually sort of like a half spin, a magnetic thing. But if you tear this off of a single wavelength, it sort of looks like a graviton might look. So we're going to take the value of the mass of a single wavelength, and you can calculate that by dividing the mass of an electron by the frequency, because that's the number of these existing in an electron, and that gives you 7.4 times 10 to the minus 48 grams. So if I hadn't shown you that before, that's the gram equivalent of a single wavelength of an electromagnetic radiation. So it's really small. So let's take this, and if we tear this off, then that's a fourth of the structure. So we'll multiply it by 1/4 right here, and then the electromagnetic relative field strength is 1/37 of the strong force. And so, and then if we take this, that's to convert this to the same range as the strong force, and if we take the force of the graviton at 6 times 10 to the minus 39th, which is comes from here, then we get this number right here. And if we multiply that by the number of grams of that single wavelength, we get 2.43 times 10 to the minus 84th of a gram. And that's super small, and you would think it would be, and much smaller than the gram equivalent of a single wavelength. It's just a silly little idea. But we need to examine the characteristics of gravity, because I want to offer an idea for dark matter. They have done all kinds of experiments with money and time to find a particle that could produce the dark matter. But really, it's just gravity. So let's call it dark gravity. Now, we've said already that it's a little half rotation of 180 degrees. And there's no charge. It's very weak, so there's no charges involved. So look at a hydrogen molecule. All the charges and things are so balanced, and if you rotate it 180 degrees, you repeat its structure. So what if the dark matter, which is dark gravity, doesn't come from some particle they can't find? What if it's just another particle of our natural matter that produces additional gravity, stronger than that 10 to the minus 39th whisper coming from somewhere? So if this could possibly produce a second source of gravity, you look at where dark matter exists in a galaxy, and it's all throughout and then out around the edges, and you can tell by the bending of the light because of its matter. Well, let the cosmologists see if they can pair that up with hydrogen molecules in far as where they correspond within the galaxy and possibly outside of it, corresponding to dark energy location. Okay. Hello, summation. I'd like to read this. I believe the first half ideas presented to be supported by strong evidence, while the second half is more speculative but interesting ideas regarding the start of the Big Bang and gravity. I do believe the ideas regarding where the four forces come from and how they operate to be correct. I like the ideas contained in the loop quantum gravity theory. I wish to comment about string theory. Every scientist knows the three problems string theory has: unobserved extra dimensions, and reduction in size and attachment to a Cabeai manifold, but this gives 10 to the 500th power plus solutions, and then using supersymmetry, which requires an entire new family of particles not observed. I wish proponents would try replacing strings with electromagnetic radiation if possible. In conclusion, the most important aspect of this presentation is the idea that matter is actually made of captured energy from radiation moving at the speed of light in a repeating revolving pattern. An even more important result is that a single wavelength of this electromagnetic radiation can represent the next step in the progression to smaller and smaller entities used to make matter, specifically molecules to atoms to fundamental particles to electromagnetic radiation's single wavelength. Talk about small, it takes 1.24 times 10 to the 20th power single wavelength to make one electron. It is the smallest amount of energy possible and is equal to Planck's constant. It has an energy gram mass equivalent of 7.37 times 10 to the minus 48 grams. My educational background is completing courses, teaching, and research in the physical chemistry PhD program at the University of Texas in Austin, Texas. I entered graduate school in 1962. This means two things. I am very old, and the research for this presentation was recently completed while retired. Thus no one to bounce ideas off of or help correct errors other than the internet. I enjoy my privacy but would like to receive feedback evaluations from scientists watching this YouTube presentation. I can receive messages at the following email address. This is seniortexan1940@gmail.com. I presently live in Orlando, Florida.